Now, before proceeding further with calculations of combining errors, we'll be learning quickly one mathematical technique which we call the binomial approximation. Now, it goes like this, that 1 plus x raised to the power n is approximately equal to 1 plus nx. Now, it's an approximation and it works fairly well provided the mod of x is very small in comparison to 1. So it doesn't always work. It works only when mod of x is very small in comparison to 1. So 1 plus x to the power n equals 1 plus nx. We can use this in this calculation, for example, 1.02 whole cube. Now, calculating the cube of this will be a time-consuming exercise, and the process can be made a little quicker if we use the binomial approximation. So 1.02 whole cube equals 1 plus 0.02 whole cube, and now you notice that this number is very small in comparison to 1. And so this is of this shape, 1 plus x to the power n, and it therefore equals approximately 1 plus nx. And eventually we end up with 1.06, which is a fairly good approximation of 1.02 whole cube. So it's an approximation, and remember, it works only subject to this condition. Now, moving on with the calculations of errors, we now take up a case where we are multiplying two physical quantities to get a third. So C here is equal to A times B, and therefore C plus minus delta C equals A plus minus delta A into B plus minus delta B. Over here we take C common and we get C times, within bracket, 1 plus minus delta C by C. And we do the same thing with this as well as this, and we have A into 1 plus minus delta A by A into B times 1 plus minus delta B by B. Now A times B is approximately equal to C. It is actually equal to C, and so C cancels with A times B, and we are left with 1 plus minus delta C by C into equals 1 plus minus delta A by A into 1 plus minus delta B by B. Now when we multiply these terms, we have 1 times 1 and delta A by A times 1, delta B by B times 1, and we have one more term which contains the product of these quantities. Now remember that errors are typically fairly small. These errors are like 1, 2, 3, 4%. And so delta A by A would be of the order of 1 by 100 or at most 1 by 20. So these are small numbers. And when we multiply very small numbers, the resulting number is very, very small. And so in this calculation, this quantity here can be easily neglected. So we neglect this and cancel 1 on each side of the equation, and we get delta C by C equals delta A by A plus delta B by B. Remember, when we are combining errors, when we are estimating the error in a calculated value, the errors are always going to be added, even if there was a minus sign here in both these quantities. Here we always add them up. As I mentioned earlier, the errors are always added, assuming that they are cumulative. They add up rather than compensate for each other. So this is the rule, sort of, that we have deduced for a multiplication. Now let's take a simple example where we are calculating area using a product of length and width. Length is given as 10.0 plus minus 0.2, and width is given as 5.00 plus minus 0.1. Both these lengths are in meter. The area is length times width for a rectangular plot, let's say, and therefore the area is length times width. So 10.0 into 5.00, which gives us 50.0 meters square. The error in the area A will be given by this equation. We just applied this result here. Delta A by A equals delta L by L plus delta W by W. And so we have this equation, delta A by A equals 0.2 by 10.0 plus 0.1 divided by 5.00. So delta A then equals, we take A onto the other side, 50.0, that's A times 2 by 100, 1 by 50, and therefore delta A comes out to be 2.00. Therefore, finally, when we report A, we say A is 50.0 plus minus 2.00. Of course, the unit is meter square, and that's one simple example on the calculation of area where we are using multiple of two lengths, where there's a multiplication involved. You use this rule. So this rule will be used whenever we are multiplying physical quantities.